we're now going to turn to a discussion of epoxides, starting with how we synthesize epoxides. Our first synthesis reaction is called epoxidation of alkenes, and it's a review reaction from the reaction of alkenes in Chapter 8. In this reaction, we start with an alkene, and we treat it with a peroxy carboxylic acid. This reacts, the alkene is converted to a single bond, and a cyclic ether ring is formed between the two carbons of the alkene. We call that cyclic ether ring an epoxide. There are several different proxy carboxylic acids that can be used. Two of the most common ones are this one, which is the peroxy acid of acetic acid, often called peroxyacetic acid or peracetic acid. This one is also very commonly used because it is a solid that is easy to handle and easy to measure and use. The name of this is metachloroperoxybenzoic acid, but most organic chemists just abbreviate it this way, MCPBA. And you're free to write MCPBA, just that acronym, over a reaction arrow to indicate that you want to use this. The second way that we can make epoxides is to take advantage of an SN2-like reaction using a halohydrin. We discussed how to make halohydrins in Chapter 8. If we start with a halohydrin like this, where we have a hydroxyl group on one carbon and on an adjacent carbon we have a halogen attached, the halogen being either chlorine or bromine, we can treat that with sodium hydroxide. And it turns out that this will cause formation of the epoxide. To understand this, we need to look at the mechanism. The mechanism is what we call an intramolecular Sn2 reaction. Intramolecular means a reaction that normally occurs between two different molecules, but in this case is occurring between two parts of the same molecule. In this case, what we're going to do is, starting with the halohydrin, the hydroxide is going to do an acid-base reaction with the hydroxyl group of the halohydrin, forming this alkoxide. This alkoxide is essentially a nucleophile. The adjacent carbon is an alkyl halide, which is essentially a substrate. So what we have is a molecule that has both a nucleophile and a substrate as part of the same chain of carbons. Because of this, the nucleophile can reach over and make a bond to the substrate alpha carbon and push out the halide leaving group all in one step. So this looks a lot like an SN2 reaction. Nucleophile attacks, pushes out the leaving group at the same time. However, it's really not correct to call it an SN2 reaction because there aren't two separate molecules. Remember that the 2 stood for bimolecular. So instead, we call this an SNI reaction. I standing for intramolecular. And we usually write a lowercase I that I like to write as a script I like that. This forms our final product. One interesting aspect of this is that there is a required stereochemistry alignment of the hydroxyl of the halohydrin and the halide of the halohydrin. Here's an example. In this case, this is a halohydrin substrate. If we look at the alignment between the hydroxyl group on one carbon and the bromine group on the adjacent carbon, they are aligned syn in the same plane. We call that syn-coplanar. That alignment is not reactive in the SNI. We need to have an anti-coplanar alignment. In this molecule, we can achieve an anti-coplanar alignment by rotating 180 degrees around this central carbon. So I've shown the right-hand portion, which has the hydroxyl, an ethyl, and a methyl, rotating 180 degrees. That creates this conformation. Notice that when the molecule rotates 180 degrees, the group that is on a dash ends up on a wedge, and the group that's on a wedge ends up on a dash. At this point then, if we deprotonate the hydroxyl, we get our desired alkoxide nucleophile, and that nucleophile can perform essentially a backside attack. It comes from the opposite side of the carbon as the leaving group is attached. This is a necessary requirement of an SN2-like reaction. So it comes from the backside, it pushes that out, and it causes inversion on this carbon. So this wedge group moves up, that dash group moves up, and we're left with this product. Epoxides are extremely useful for synthesis reactions because they can be opened with nucleophiles and create a product that has a nucleophile attached on one carbon and then a hydroxyl group on another carbon, which either might be the desired functional group or can be used to introduce other groups and other pieces. We're going to look at two ring opening reactions of epoxides that use complementary conditions. The first is going to be ring opening using acid conditions. We use this when we have low basicity nucleophiles, what we would normally call like low reactivity weak nucleophiles. The nucleophiles that are on the bottom two rows of our SN1, SN2, E1, E2 chart. If we look at these then, we would have an epoxide, we would have a low basicity nucleophile that in many cases, most cases even, would have a hydrogen attached, and an acid. We would use an acid like sulfuric acid or even acetic acid, or there's a variety of acids we could use. At the end of the reaction, the epoxide would be open, the oxygen would be protonated, and the nucleophile would be attached, and if the nucleophile had a hydrogen, that would have been deprotonated. Here's the mechanism of that reaction. Because it's an acid promoted reaction, what we're going to do is we're going to do acid-base reaction as our first step. Almost all reactions that have acid as part of the reagents will do acid-base reaction in the first step because acid-base reaction is so fast. I'm going to use a generic acid here to represent the acid. So I write a generic acid as hydrogen attached to a base. In theory, there would be a specific acid, but that would depend a lot on specifically what nucleophile we are using. And in fact, it doesn't really matter. We just need to know that there is an acid. In the first step then, the oxygen lone pair will react with the hydrogen of the acid in an acid-base reaction. It'll make a bond to that hydrogen, and a pair of electrons will be pushed out onto the base on the other side. We'll get a protonated form of the epoxide where the oxygen has a positive charge. Because of both the electronegativity of the oxygen and the positive charge, there's going to be a lot of, because the oxygen is electronegative and it has a positive charge, it will be pulling very hard on the bonds connected to these carbons, making them very polar bonds with very large partial positives on the carbon. The nucleophile will become attracted to one of these partial positives and make a bond. In order to make room for that, the bond to the oxygen will have to be broken. That will open the epoxide ring. So we get this intermediate, where we have an OH hydroxyl group on one carbon and the nucleophile attached. If the nucleophile is neutral and has a hydrogen, then it will have a positive charge, and we can remove that positive charge by having the base deprotonate that nucleophile, creating our final product. So, some notes. First, when acid is a reagent in an observed reaction, the first step of the mechanism will almost always be a protonation reaction. We're going to use acid with weakly basic nucleophiles like water, alcohols, and the halides. And if the nucleophile is uncharged like water, we will have an additional deprotonation step. Halides do not need a deprotonation step. If we have an epoxide that is unsymmetric, then we have the possibility of having regioselectivity, one carbon of the epoxide preferring to react with the nucleophile. In the acid-promoted reaction, generally the nucleophile prefers to attack the most substituted carbon. Here's an example. If we look at this epoxide, the left carbon has 2 carbon groups, the right-hand carbon has 2 hydrogens, so the left carbon is clearly more substituted. In our first step, we protonate the epoxide. I've put this HB because I kind of combined all of the reagents over the arrow here. So would be either concentrated H2SO4 or possibly the protonated form of the alcohol acting like the acid. We're just going to write HB. We protonate the epoxide, we get our protonated intermediate. We have large partial positives on these carbons because the oxygen is pulling so hard on the bonds. If we look then, we have a positive charge or a partial positive charge on this carbon, which is tertiary, and we have a partial positive charge on this carbon, which is primary. It turns out that the epoxide does not have to stay symmetric, and in fact, in this case, the oxygen leans toward the less substituted carbon. That weakens the bond between the oxygen and the more substituted carbon, and it creates a larger partial positive charge on the more substituted carbon. That's desired because more substituted carbocations have a lower potential energy. Because then this has the larger partial positive charge, the nucleophile would prefer to react with the more substituted carbon, opening the ring. And then again, because we're using a neutral nucleophile, it becomes positively charged. We deprotonate it, and we get this product. The significance of this product is that if we look, the ether OCH3 alkoxy group is on the more substituted carbon, and the hydroxyl group is on the less substituted carbon. There's also a stereochemistry requirement for these epoxide ring openings. They go by essentially backside attack. The nucleophile attacks from the face opposite the oxygen of the epoxide. We can see this very clearly in this example, which has an epoxide attached to a ring. The epoxide is attached with wedge bonds to the top face of the ring, and the substituent hydrogen and methyl group are attached with dash bonds. If we treat this with the same reagent that we used above, methanol and concentrated H2SO4, the methanol is going to attach to the more substituted carbon, as we discussed, but in that process, it's going to do inversion. So as it attaches and breaks the bond from the backside, the methyl group will be pushed from a dash onto a wedge, and we will get this anti-stereochemistry right here. We also can do ring opening under what we call base conditions. Base conditions uses reagents that have a high amount of basicity and, most specifically, no acid. We add acid later in a second step after the first step is complete. This is going to use nucleophiles from the first two rows of our table. It's also going to include, as we'll see later, the strong carbon nucleophiles like Grignard reagents, alkyl lithiums. In this reaction then, we first take our negatively charged basic nucleophile and allow it to react with the epoxide. Then we protonate the product with hydronium, ending up with hydroxyl on one, nucleophile on the other carbon. The mechanism looks like this. In some ways it's a less complex mechanism than the acid one. Because the nucleophile should react directly with the epoxide, we don't need to protonate first to increase the reactivity. So nucleophile comes over, makes a bond to the carbon because of the partial positive charge. That pushes the bond between the carbon and oxygen out onto the oxygen, forming an alkoxide. When that's all done, then in a separate step we can add hydronium in what we call a hydrolysis step. The alkoxide, strong base, will do acid-base reaction with the hydronium ion and become protonated. One of the important distinctions between the base and the acid conditions is the regioselectivity. The base conditions are much more like an Sn2 reaction. Recall that Sn2 reactions are strongly affected by steric hindrance. So what we see is, in the base conditions, the nucleophile prefers to attack the less hindered, less substituted carbon. So, for example, if we use the same example epoxide that we used in the acid conditions above, and we actually use a nucleophile that is related to the weak methanol nucleophile we used, where we deprotonate the methanol and give it a negative charge as a methoxy group. We can see that the methoxy group would then prefer to make a bond to the less substituted carbon and attach on the right-hand side. That would open the ring and leave a negative charge on the oxygen, which then when we put in hydrolysis step would become protonated, and we would get this product. If we compare this product to the product above from the acid-catalyzed opening, you can see that the position of the hydroxyl group and the methoxy group are reversed. So what this means is that this is complementary. We can put the nucleophile, in theory, depending on the nucleophile, on either carbon as desired, depending on what conditions we use. This reaction also has anti-addition. The nucleophile attacks from the backside, which we should expect from its very Sn2-like nature, but it attacks on the less substituted side. So again, the methoxy group would attack here from the backside, the epoxide would open, it would become protonated in a separate step, and significantly there would be inversion, which would force this hydrogen, which is currently on a dash, onto a wedge, and the nucleophile would be on a dash. Finally, one really important application of this is to open epoxides with Grignard reagents, alkyl lithiums, and even acetylide ions, like we saw in Chapter 9. The Grignard reagents react pretty well generally with these epoxides. They prefer to attack on the less substituted side, and they require a hydrolysis step. And what this allows us to do is add a carbon group onto one side of the epoxide and then have a CH2 or some other carbon group with a hydroxyl on the second carbon. This is a really useful method in many cases when we need to build a carbon chain. We can also use alkyl lithiums for this. The alkyl lithiums basically come with lithium halide like lithium bromide. That's actually needed to kind of help the epoxide open. And again, we do a hydrolysis step. Finally, we can use lithium acetylides or sodium acetylides, although lithium are more commonly used. But to use these, we have to add this Lewis acid, BF3. This acid coordinates with the oxygen, makes the epoxide more reactive so that the acetylide ion can react and open it up.